Certainly. Mathematics plays a crucial role in logical arguments and reasoning. It provides a formal language and a set of tools that allow for precise and rigorous analysis of logical relationships and deductions. Here are some key aspects of mathematics used in logical arguments. 1. Symbolic language. Mathematics often employs a symbolic language to represent logical relationships and statements. Symbols such as letters, variables, and mathematical operators are used to express propositions, connectives such as and, or, not, quantifiers such as for all and there exists, and logical operations. This symbolic language helps to eliminate ambiguity and allows for concise and precise expression of logical ideas. 2. Formal systems. Mathematics provides formal systems, such as propositional logic, predicate logic, and set theory, that have well-defined rules and axioms governing their manipulation. These formal systems establish a framework for logical reasoning and allow for the systematic analysis of logical arguments. 3. Logical connectives. Mathematical notation is often used to represent logical connectives, such as conjunction, logical and, disjunction, logical or, negation, logical not, implication, logical if, then, and equivalence, logical if and only if. These connectives allow for the construction of complex logical statements and the analysis of their truth values. 4. Quantification. Mathematical notation also provides symbols for quantification, such as the universal quantifier, for all, and the existential quantifier, there exists. These symbols allow for the expression of statements that involve all elements of a set or at least one element of a set, respectively. Quantification is crucial in formalizing logical statements and reasoning about general properties. 5. Proof theory. Mathematics offers a rigorous framework for constructing and analyzing proofs. Proof theory provides a set of rules and techniques for demonstrating the validity of logical arguments and theorems. Mathematical proofs are often structured using logical principles, such as axioms, definitions, and logical inference rules, to establish the truth of mathematical statements. 6. Formal verification. In areas such as computer science and artificial intelligence, mathematical methods are employed to formally verify the correctness of logical systems, algorithms, and software. Formal verification involves using mathematical techniques, such as model checking and theorem proving, to ensure that logical arguments and systems adhere to specified properties and constraints. By employing mathematics within logical arguments, we can achieve greater precision, rigor, and clarity in our reasoning. Mathematics provides a powerful framework for analyzing the structure and validity of logical statements, enabling us to make reliable deductions and draw sound conclusions. Certainly. Symbolic language plays a central role in logical arguments as it provides a concise and precise way to represent the structure and relationships of logical statements. Symbolic notation allows for the manipulation and analysis of complex logical expressions, aiding in the formalization and rigorous examination of logical arguments. Here are some key aspects of symbolic language in logical arguments. 1. Propositional logic symbols. In propositional logic, symbols are used to represent propositions, which are declarative statements that can be either true or false. Common symbols used in propositional logic include variables. Variables, often represented by letters e.g., p, q, r, stand for propositions. They can take on the values of either true or false. Logical connectives, symbols such as and, conjunction / and, or, disjunction / or, negation / not, implication / if, then, and left-right arrow, equivalence / if and only if, represent logical connectives that combine propositions to form compound statements. Parentheses. Parentheses are used to group propositions and determine the order of evaluation. They help clarify the intended structure and precedence of logical operations. 2. Predicate logic symbols. Predicate logic extends propositional logic by incorporating symbols that represent quantifiers, for all for universal quantification and there exists for existential quantification, and predicates, statements with variables that become propositions when specific values are assigned. Universal quantifier. The symbol for all, read as for all or for every, is used to express that a statement holds true for every element in a given domain. Existential quantifier. The symbol there exists, read as there exists, is used to express that there exists at least one element in a given domain for which a statement holds true. Predicates. Predicates are symbols that represent properties or relations involving variables. They become propositions when specific values are assigned to the variables. 3. Logical inference rules. Symbolic language is also employed in the representation of logical inference rules. These rules define valid patterns of reasoning and allow for the derivation of new logical statements from existing ones. Symbols, such as right-tack, turnstile, are used to denote the logical entailment or implication between premises and conclusions in logical arguments. 4. Formalization and proof. Symbolic notation is particularly useful in formalizing logical arguments and constructing proofs. By representing statements and logical relationships with symbols, complex arguments can be broken down into a series of logical steps, making it easier to identify patterns of inference and establish the validity of logical reasoning. Symbolic language in logical arguments provides a notation system that enables logical statements to be expressed concisely and precisely. It allows for the manipulation and analysis of logical expressions, the formalization of arguments, and the construction of rigorous proofs. By employing symbolic language, logicians are able to investigate the structure and validity of logical statements in a systematic and rigorous manner. Certainly. In logical arguments, formal systems play a crucial role in providing a rigorous framework for analyzing and evaluating the validity of logical reasoning. Formal systems are sets of rules, symbols, and axioms that define the structure and manipulation of logical expressions. Here are some key aspects of formal systems in logical arguments. 1. Syntax. A formal system has a specific syntax, which governs the formation and well-formedness of logical expressions within the system. The syntax specifies rules for constructing propositions, defining logical connectives, and specifying the order of operations. By adhering to the syntax, one can ensure the validity and consistency of the expressions. 2. Symbols. Formal systems employ symbols to represent various elements of logical expressions. These symbols include variables, logical connectives, such as conjunction, disjunction, negation, quantifiers, and parentheses. The symbols provide a concise and unambiguous representation of logical relationships. 3. Axioms. Axioms are fundamental statements or principles that are assumed to be true within a formal system. They serve as starting points from which logical reasoning proceeds. Axioms provide the foundation for deducing new statements and are typically self-evident or intuitively accepted within the context of the formal system. 4. Inference rules. Inference rules are the logical rules of deduction within a formal system. They define valid patterns of reasoning that allow the derivation of new statements from existing ones. Inference rules specify the conditions under which a conclusion can be drawn based on given premises. Examples of common inference rules include modus ponens, universal instantiation, and disjunction elimination. 5. Proof theory. Formal systems provide a framework for constructing and analyzing proofs. Proof theory deals with establishing the validity of arguments and theorems within a formal system. It involves following a set of rules and logical steps to demonstrate that a conclusion logically follows from a given set of premises. Proof theory ensures the reliability and correctness of logical reasoning. 6. Consistency and completeness. Formal systems aim to achieve consistency and completeness. Consistency means that a formal system does not allow for the derivation of contradictory statements. Completeness, on the other hand, means that the formal system is capable of expressing and proving all valid statements within its domain. Achieving both consistency and completeness is a fundamental goal in the development of formal systems. 7. Examples of formal systems. There are several well-known formal systems used in logical arguments, such as propositional logic, predicate logic, including first-order logic, modal logic, and set theory. Each formal system has its own set of rules, axioms, and symbols that define its specific logical language and structure. Formal systems provide a rigorous and systematic approach to analyzing and evaluating logical arguments. They establish a framework for expressing logical relationships, deducing new statements, and proving the validity of logical reasoning. By employing formal systems, logicians can ensure the precision, consistency, and reliability of logical arguments. Certainly, logical connectives are fundamental components in logical arguments that allow us to combine and manipulate propositions. They serve as building blocks for constructing complex logical statements. Here are some key logical connectives commonly used in logical arguments. 1. Conjunction, logical and the conjunction connective, often represented by the symbol and or the word and, combines two propositions into a compound statement. The resulting compound statement is true only if both of its component propositions are true. For example, if proposition A represents it is raining and proposition B represents the ground is wet, the conjunction A and B would be true if both statements are true, meaning it is raining and the ground is wet. 2. Disjunction, logical or the disjunction connective, often represented by the symbol or the word or, combines two propositions into a compound statement. The resulting compound statement is true if at least one of its component propositions is true. For example, if proposition C represents the sun is shining and proposition D represents the sky is blue, the disjunction C or D would be true if either statement is true, meaning the sun is shining or the sky is blue. 3. Negation, logical not the negation connective, often represented by the symbol or the word not, negates or reverses the truth value of a proposition. It produces a compound statement that is true when the original proposition is false and false when the original proposition is true. For example, if proposition E represents it is sunny, the negation E would be true if it is not sunny, meaning it is not sunny. 4. Implication, logical if, then the implication connective, often represented by the symbol or the phrase if, then, establishes a conditional relationship between two propositions. It states that if the first proposition, the antecedent, is true, then the second proposition, the consequent, must also be true. If the antecedent is false, the implication is considered vacuously true. For example, if proposition F represents if it is raining, then the ground is wet, the implication FB would be true if it is not raining or if the ground is wet. 5. Equivalence, logical if and only if the equivalence connective, often represented by the symbol left-right arrow or the phrase if and only if, expresses a biconditional relationship between two propositions. It states that the two propositions have the same truth value, they are either both true or both false. For example, if proposition G represents 2 plus 2 equals 4 and proposition H represents 4 is an even number, the equivalence G left-right arrow H would be true since both propositions are true. Logical connectives allow us to form complex logical statements from simpler propositions and analyze their truth values. They play a crucial role in constructing logical arguments, expressing relationships between statements, and drawing logical conclusions. By utilizing logical connectives effectively, we can evaluate the validity and coherence of logical reasoning. Certainly, quantification is an essential aspect of logical arguments that allows us to make statements about groups of objects or individuals. It involves the use of quantifiers to express the scope and extent of a statement. There are two main types of quantifiers used in logical arguments: universal quantification, for all, and existential quantification, there exists. Here's an explanation of each. 1. Universal quantification, for all. Universal quantification, represented by the symbol for all, read as for all or for every, expresses that a statement holds true for every element in a given domain. It asserts that a property or condition applies to every individual or object under consideration. For example, for all x p, x can be read as for all x p, x, where p, x represents a predicate statement about x. This means that the predicate p, x is true for every x in the domain. Universal quantification is often used to make general statements and establish broad implications. It allows us to reason about all members of a set or all possible instances of a condition. For instance, for all natural numbers n plus 1 is greater than n can be expressed using universal quantification as for all n is an element of n plus 1n, stating that this property holds true for every natural number. 2. Existential quantification, there exists. Existential quantification, represented by the symbol there exists, read as there exists, asserts that at least one element in a given domain satisfies a particular condition or has a specific property. It indicates the existence of an object or individual for which a statement is true. For example, there exists x p, x can be read as there exists an x such that p, x, meaning that there is at least one x in the domain for which the predicate p, x is true. Existential quantification is used to establish the existence of something or to make specific claims about at least one instance. It allows us to reason about the presence or occurrence of certain elements within a set or the availability of solutions to a problem. For instance, there exists a prime number greater than 100 can be expressed using existential quantification as there exists n greater than 100 and prime, n, indicating that such a prime number exists. Quantification plays a crucial role in formal logic, mathematics, and various fields of study. It enables us to express statements about entire sets, groups, or collections of objects, as well as to reason about their properties and relationships. Universal and existential quantification provide a powerful framework for making generalizations, establishing existence claims, and formulating precise logical arguments. Certainly, proof theory is a branch of logic that deals with the construction and analysis of formal proofs in logical arguments. It provides a systematic method for demonstrating the validity of logical reasoning within a given formal system. Here are some key aspects of proof theory in logical arguments. 1. Formal systems. Proof theory operates within formal systems, which consist of a set of rules, symbols, and axioms that define the structure and manipulation of logical expressions. These formal systems include propositional logic, predicate logic, modal logic, and others. Each formal system has its own specific rules of inference and axioms. 2. Proofs as derivations. In proof theory, a proof is viewed as a formal derivation, a sequence of logical steps that start from a set of premises and arrive at a conclusion. The steps in a proof are constructed according to the rules of inference and axioms of the formal system. Each step follows logically from the previous steps, leading to the desired conclusion. 3. Inference rules. Inference rules are the logical rules of deduction within a formal system. They define valid patterns of reasoning that allow the derivation of new statements from existing ones. inference rules specify the conditions under which a conclusion can be drawn based on given premises. Examples of common inference rules include modus ponens, universal instantiation, and disjunction elimination. 4. Axioms. Axioms are fundamental statements or principles that are assumed to be true within a formal system. They serve as starting points from which logical reasoning proceeds. Axioms provide the foundation for deducing new statements and are typically self-evident or intuitively accepted within the context of the formal system. 5. Proof construction. Proof theory involves the systematic construction of proofs using inference rules and axioms. The goal is to demonstrate that a conclusion logically follows from a given set of premises. Proof construction involves applying inference rules, making logical connections between statements, and ensuring the validity of each step in the derivation. 6. Soundness and completeness. Soundness and completeness are important properties of proof systems. Soundness means that if a statement is provable within a formal system, then it is logically valid. Completeness means that if a statement is logically valid, then it is provable within the formal system. Both soundness and completeness ensure the reliability and correctness of the proof system. 7. Formalization of mathematics. Proof theory plays a crucial role in the formalization of mathematics. By providing a rigorous framework for constructing and analyzing proofs, proof theory ensures the validity and coherence of mathematical arguments. It allows mathematicians to establish the truth of mathematical statements and theorems through logical reasoning. Proof theory provides a formal and systematic approach to examining the validity of logical arguments. By employing rigorous rules of inference and axioms, proof theory allows us to construct valid and reliable proofs within formal systems. It is a fundamental tool in logic, mathematics, and other fields where logical reasoning is essential. Certainly. Formal verification is a process that uses formal methods and techniques to rigorously analyze and confirm the correctness of logical arguments, systems, or software. It aims to provide mathematical certainty and assurance that a system or argument behaves as intended. Here are some key aspects of formal verification in logical arguments. 1. Formal methods. Formal verification relies on formal methods, which are mathematical techniques and tools for specifying, modeling, and analyzing systems. Formal methods use precise mathematical languages, such as formal logic or mathematical notation, to describe the behavior and properties of systems. These methods provide a rigorous and unambiguous framework for reasoning about the correctness of systems. 2. Specification. In formal verification, a formal specification is created to define the desired behavior and properties of the system or argument being analyzed. The specification captures the essential requirements and constraints that the system should satisfy. It serves as a reference against which the system's behavior is evaluated during the verification process. 3. Model checking. Model checking is a formal verification technique that exhaustively analyzes the behavior of a system by systematically exploring all possible states and transitions. It verifies whether a given system model satisfies a set of specified properties or requirements. Model checking is particularly useful for verifying finite state systems, such as digital circuits or software programs. 4. Theorem proving. Theorem proving is another formal verification technique that uses logical reasoning to establish the correctness of a system or argument. It involves constructing formal proofs within a specified logical system to demonstrate that certain properties hold true. Theorem proving can be done manually or with the assistance of automated theorem provers, which are computer programs that help verify the validity of logical statements. 5. Formal verification tools. Various computer-aided tools and software are available to support formal verification processes. These tools use formal methods, model checking algorithms, or automated theorem provers to analyze systems and verify their correctness. Formal verification tools can detect errors, inconsistencies, or violations of specified properties, helping ensure the reliability and robustness of systems. 6. Verification of safety and liveness properties. Formal verification often focuses on verifying safety and liveness properties of systems. Safety properties express that something bad will never happen, while liveness properties state that something good will eventually happen. By verifying these properties, formal verification ensures that critical aspects of a system, such as absence of errors or progress, are guaranteed. 7. Application areas. Formal verification is widely used in various domains, including hardware design, software engineering, cybersecurity, critical systems, e.g., aviation or healthcare, and formal methods research. It helps identify and rectify design flaws, detect bugs or vulnerabilities, and establish the correctness of complex systems or arguments. Formal verification plays a crucial role in ensuring the correctness, reliability, and safety of systems or arguments. By employing formal methods, model checking, theorem proving, and specialized tools, it provides a systematic and mathematically rigorous approach to analyzing and confirming the validity of logical arguments or the behavior of systems. Formal verification helps mitigate risks, increase confidence, and improve the quality of complex systems in various application domains. Certainly. In this session, we discussed several topics related to logic and formal methods. Here's a summary of the key points covered. 1. Quantification in logical arguments. We explored quantification, which involves using universal, for all, and existential, there exists, quantifiers to express the scope and extent of statements in logical arguments. Universal quantification, for all, states that a property holds true for every element in a domain, while existential quantification, there exists, asserts the existence of at least one element satisfying a condition. 2. Proof theory in logical arguments. We discussed proof theory, which is concerned with the construction and analysis of formal proofs in logical arguments. Proof theory involves formal systems, proofs as derivations, inference rules, axioms, and the systematic construction of proofs to demonstrate the validity of logical reasoning. 3. Formal verification in logical arguments. We explored formal verification, which uses formal methods and techniques to rigorously analyze and confirm the correctness of logical arguments, systems, or software. It involves formal methods, specification, model checking, theorem proving, formal verification tools, and the verification of safety and liveness properties. These topics provide insights into different aspects of logical reasoning, the construction of formal proofs, and techniques for ensuring the correctness and reliability of systems or arguments using formal verification methods. Is there anything else I can assist you with?